Okay, so we're talking about this ideal gas law, and I want to let you know a very important thing. For today's homework, the homework that I assigned today, the homework I assigned today that's due on Wednesday, we are going to have to check our gases and see what our gases are. Are they a real gas or are they an ideal gas? We're going to check it on that generalized compressibility chart. Okay, we're going to have to use that. But after today, in the lecture that happens next week, you will not have to check to see if z is equal to 1. You are going to assume. The problem statement is going to tell you something like air as an ideal gas or oxygen as an ideal gas, or you're going to assume that you have an ideal gas, and you can use this ideal gas equation, because once we assume that it's an ideal gas, a whole realm, a whole world of possibilities comes up to us. Okay, but today's homework, you're going to have to choose that. Now, the next thing I'm going to say is that we will assume ideal gases for carbon monoxide, carbon dioxide, helium, argon, oxygen, neon, and air. We are going to see that these are going to be ideal coming on Monday for the rest of the semester. Now, why are they ideal? You will say, okay, because the compressibility factor, if I did the calculations, would give me a value of z is equal to 1. All right, I want to do one example here with us at how we're going to use this table, because sometimes it's very simple to use, but it can cause some concerns with students here. So what we want to do here is we want to, our example problem is we want to define the volume in meters cubed occupied by 2 kilograms of water vapor at 100 bar and 400 degrees Celsius. Okay, and we're going to do two things. We're going to do this with the generalized compressibility, and B, we're going to use the steam tables. Okay, so up until today, if I ask you for the volume, if I ask you this problem, find the volume of meter cubed occupied by 2 kilograms of water in a 100 bar 400 degrees Celsius, you would check the state. You would find it's a vapor. You would go to your vapor tables and you would find out what your value is. Okay, very easy. Okay, let's just go ahead and do that right now. I'm gonna do part B first. Part B first. So I am going to go to 100 bar. Open my document camera here. 100 bar. And I'm going to go to 400 degrees Celsius. Here's 400 degrees Celsius. I'm going to read off my specific volume here. This is going to give me my specific volume is equal to 0.02641 meters cubed per kilogram. We know that's true. We're comfortable with that. We've done that. We're pretty practiced on that. But now we have this new idea how to do this with the generalized compressibility chart. Okay, so here's what we're going to do. The first thing to do is we want to find out what TR is, which is equal to the temperature divided by the critical temperature. And we have to find out what PR is, which is the pressure divided by the critical pressure. That's the first thing we need to do. So TR here, we're going to say 400 degrees Celsius. Remember, we have to add 273 here. And we're going to divide that by, well, let's go to our table A1. Table A1, document camera, table A1 for air. It's a little blurry here. Come on. If you can't read that, it's 133. It's 133, so that is going to be the critical temperature. Okay. Oh, it's water. Water. You're yelling at me from it's water. Ah. 647.3. 647.3. I thought something doesn't feel right about this. And then our pressure is going to be equal to 100 bar divided by the critical pressure here. That's going to be 220.9. 220.9. Let's go back here. 220.9. 220.9 bar. And if we do this, we get that our reduced temperature is going to be 1.04, and our reduced pressure is going to be equal to 0.45. Okay, now we go to our generalized compressibility chart. Okay, generalized compressibility chart. And we pull it up here. 1.4, remember 1.04 and 0.45. Remember that. We go to our document camera and we're going to go for 1.04. Now notice here are my lines of constant of TRs, and we have 1.05, but we don't have a 1.04, so we have to see, this is 1.0, so we have to see it's somewhere a little bit below there. We're going to have to make a little assumption where we are. Okay, and then we're going to look for a reduced pressure of 0.45, which is on this line here, and we're to see where they intersect. I get, it's a little bit up here. I'm going to say it's my Z value is 0.86. If you would have done 0.85, I would probably went with you and said that's good. But I'm going to say my Z value is 0.86. Okay, 0.86. And so what I now know is Z is equal to PV over RT. Okay, and I want to find out, what am I trying to find out? What is my specific volume? So I know that my specific volume is going to be Z times R times temperature all over my pressure. Okay, so what do I have to do here? For my Z value, I'm going to use 0.86. For my R value, I'm going to use R bar divided by the molecular weight of H2O. For my temperature value, what am I going to use? Am I going to use 400? No. Remember, whenever we deal with this equation, it has to be has to be in Kelvin. So 400 plus 273, and my pressure down here, I'm going to want to use 100 bar. But I have to convert this, so my units all have to work out here. So this is going to be in units of meters cubed per kilogram. Okay, I'm going to ask you to do this. This is going to be your quiz question for today. And you're going to find a value that it should be reasonably close to the value that we would have found in the steam tables. And you might ask the question, so Dr. Wanklyn, why? If the values on the steam tables are they're the right values. Absolutely, they are smack on right values. Why would you ever use generalized compressibility? Okay, maybe you don't want to carry around a big stack of steam tables. Maybe you only want to carry around a list of molecular weights and critical temperatures and critical pressures, and a couple charts that you could go and find these values off of. We could do that. We could get a pretty good values for how we could work and find out what our specific volumes are. Not carrying around, and we could do it for any gas. We wouldn't really have to worry about having stacks and stacks of tables. We could do it for any gas, and we could get a reasonably good number, value that we could use. Now, if you would notice here that my Z value is 0.86, that's away from 1. We can't consider water, vapor here to be an ideal gas. It's not close enough to 1. But we can, coming up, we can say that some gases the Z is close enough to 1 that, this approximation, this modeling things as an ideal gas gets us so darn close to the actual values that we will use them as we go through and study through our material. So this is a very important lecture to talk to us about generalized compressibility and what it means, and how we are looking with real gases. Every time we dealt with water, vapor, R22, R134A, propane, and ammonia in a vapor state, we were dealing with them as a real gas. Here, when generalized compressibility, when Z is not equal to 1, we're considering in a real gas. But starting next week, now we're going to say, but most of the time, the z-values for these set of gases is going to be so dang close to 1 that it would just simplify our life just to assume, yes, yes, our calculations are going to be a tad off from the actuality, but what's going to happen there is in assuming ideal gas, in accepting that small bit of difference from what the number actually is, we can eliminate a huge amount of calculations. So, which you can mess up anyway. So that ideal gas assumption is a very powerful assumption that we'll be taking advantage of. But and I know you can hardly wait, but we're going to have you wait over the weekend until Monday so we can talk about that together. Until then, have a happy and healthy weekend, and we'll see you back here. And go Cats.